we are going to start with the definition of moment of inertia. Because section 3 is about rotational motion, and as object is rotating, sometimes it resists to rotation, to start the rotation. If object is in rotation, it resists to stop the rotation. So, difficulty or position of an object to rotational motion is named as moment of inertia. So, the moment of inertia is a measure of object's resistance to change in its rotational motion. In fact, this definition explains everything. So, object resists to make a change in its rotational motion. So, how can we change rotational motion? If an object is rotating, you try to stop it. It doesn't want to stop. Bounded resistance is this. Or if object is at rest, it does not want to start rotation. It resists to start rotation. Yeah, it's object's resistance to make any change in its rotational motion is known as moment of inertia. And its symbol is capital I. And it's the rotation analog of mass. What does this mean? In translational motion, mass resists object to change in translational motion. Yeah, if you want to accelerate an object, it resists to accelerate, to speed up or slow down. If object is in motion, it does not want to stop moving. So this is resistance inertia in translational motion, but we have moment of inertia as resistance in rotational motion. That's why we say that they are analog to each other. They have equivalent effects. Mass has an effect in translational motion, which is the resistance to the motion. The other one is in resistance in rotational motion. It resists to change in rotational motion. It's usually kilogram meter square by this, so when we are studying the shape of an object, we are going to define that. And moment of inertia depends on three parameters. One of them is absolute mass. If the object is a very big mass, it will resist to start motion, big mass. It's not easy to rotate it. So, if mass increases, moment of inertia of the object absolutely increases. Second one is distribution of mass. Yani how close the mass to the axis of rotation. How far the mass from the axis of rotation. Best example is rotating a pen. So you can rotate it very, very easily if it is close to the center, which is the distribution of mass is very close to axis of rotation. If you make it like this, rotation becomes not that easy. So this is harder than that one, because when you do like this, distribution of mass gets away from the axis of rotation, so moment of inertia increases. Second factor which affects the moment of inertia, how close the mass to the axis of rotation, yani distribution of mass. And the farther the mass of the object from the axis of rotation, which means distribution is farther, the more difficult it is to rotate the object, and moment of inertia is greater, the greater the object's moment of inertia. Two factors which affect moment of inertia is mass and how this mass is distributed with respect to axis of rotation. It's close or far. If it is far, big moment of inertia. If it is close, small moment of inertia. And third factor is shape. Shape is in fact related to distribution of mass somehow, but studying as a different title is okay. Yani, moment of inertia depends on three factors. One of them is mass, the other one is distribution of mass, the third one is the shape of the object. This table is moment of inertia of different shapes from greatest moment of inertia to smallest moment of inertia. One of them is point mass above line axis. You know what point mass is. If an object is in circular motion, we treat the object as a point mass. Any circular motion will have a moment of inertia equation mr squared. M is mass of the object in circular path, really r is the radius of the circular path. And second one is the theorem about symmetry axis. Best example is bicycle wheel. Bicycle wheel, if it's rotated about the center, so it is theorem about symmetry axis. Symmetry axis is the line which passes through the center. It's called symmetry axis. Bicycle wheel or steering wheel of an automobile also can be taught as theorem about symmetry axis. mr squared. Both have moment of inertia equation mr squared. In here m is the mass of the tunnel. bicycle, or the radius of the bicycle or tino. Second shape which has a bit less moment inertia is spherical shell, 2 over 3 mr squared, which is m mass again of the spherical shell. It's like football, basketball, inside must be empty. And it's going to rotate about an axis passing through the diameter. And the other one is disc and cylinder. They have same moment inertia, 1 over 2 mr squared. It's, as you see, smaller. This one is the coefficient is 1. In here, this is equal to 0.66. This one is 0.5, 1 over 2 mr squared. M is the mass of the disc or cylinder. R is the radius of the disc or cylinder. And also, tino about diameter also has 1 over 2 mr squared. What is it? In fact, same thing. Tino, bicycle with bicycle. But in here, it's rotating about the center, just like bicycle. In here, you are going to rotate the bicycle around its diameter. So I forget to bring it, but if I make it, this is a hoop like this, and let's make a hoop. Alright, this is a similar to L. So you are in the first one, you are going to rotate it this way, about the center. But in here, you are going to rotate it like that. Till about diameter. As you see, it has less moment of inertia, 1 over 2 mr squared. Yani, rotating this way is easier than that way. Last one is the solid sphere about diameter, baseball, bowling ball, and anything inside is at full. 2 over 5 mr squared, and this 2 over 5 is 0.4. M is the mass of the sphere, R is the radius of the sphere. These are the shapes which has mass and radius. And also we have a few more shapes in the book where we're given. One of thin rod, like a pen. The first one is thin rod about perpendicular axis to the M. You are going to rotate it from the M in this case. Moment of inertia is going to be M 1 over 3 ml squared. M mass of the pen and rod. L is the length of the rod. And the other one is 1 over 12 ml squared. So mass of the rod and length of the rod. As you see, this one is harder. 1 over 3. This is 1 over 12. As you see, this is harder. How many times harder? 4 times. As I said, moment inertia determines how easy or how difficult to rotate the object is. And how easy and how difficult rotating an object is about how much force you apply. And force you apply on an object in rotational motion produces a torque. In fact, moment inertia determines how big torque you need to rotate an object. If moment inertia is greater, you need a greater torque to make the same acceleration. Just like in Newton's second law of motion, if the mass is increasing, so you need a big force to start the rotation of the same acceleration. Similarly, if moment of inertia increases, it's going to be hard to rotate. You need a big torque to start this rotation with the same acceleration. This is known as Newton's second law for translational motion. This is Newton's second law for rotational motion. And just like in here, mass is a scalar quantity. Moment inertia is also a scalar quantity. Just like in here, acceleration is a vector quantity, linear one, and force is a vector quantity. In here also same. Alpha is a vector quantity, torque is a vector quantity, and whatever the sign of alpha is, force and the torque will have the same sign. Yani, a positive net torque produces a positive angular acceleration alpha. Negative net torque produces a negative angular acceleration alpha. Okay? Then, a problem. This is the one which is asked in this frequently. A force of magnitude 2 Newton is applied tangentially. You know, tangent line is perpendicular to radius. To a disc of mass 5 kilogram and radius is 0.1 meter. What is the angular acceleration alpha? So, angular acceleration depends on 2 factors. One of them is how big the moment inertia is. Second one is how big your torque is. So, torque is equal to I times alpha. To calculate angular acceleration, demonstration. I need to know how much is angular torque. I have to calculate first this. Second one is I need to know how much is the moment of inertia. Torque can be calculated because this curved force has a 2 Newton and applied tangentially to the disc. So this is how it is applied, which is 2 Newton, and this is the axis of rotation. Distance from force to axis of rotation, this distance is 0.1 meter. So I can calculate how much torque is produced on the disc by using definition of the torque. What was the equation? Ft sine theta. Sine theta, sine 90 is in here 1, so I don't need to write it. So I can find how much is the torque produced. F times D. F is 2. Distance is 0.1, so it becomes 0.2 Newton meter is the torque. I found this. I will insert it here, but I also know how much is moment of inertia. So I is equal to, for disc, moment inertia 1 over 2 mr squared. So 1 over 2 m is 5, r is 0.1 squared. We will find the answer as I think it's going to be 0.025. 0.025 kilogram meter squared. So after that we are going to insert this in this equation and we will find how much is alpha. 0.2 is equal to 0.025 times alpha. Then it's going to be easy. That's almost 200 divided by 24 is 8. Alpha is going to be 8 radian per second squared. Which means alpha depends on two things, two parameters or two quantities. One of them is how big the moment of inertia is, I. The second one is how big the torque is. And the equation tells you that if you want to get the same alpha for two different objects, different moment of inertia, if moment of inertia is big, we need a greater torque to make the same acceleration. And next quantity was angular momentum. Angular momentum, linear momentum, they are very, again, close to each other. What momentum is first? Let's get it. Momentum, in fact, defines how strong a motion is. It defines the motion effect. And in the 11th grade, you define the linear momentum. Linear momentum, mass and velocity. Mass, big momentum. Big velocity, big momentum. So that's why linear momentum was mass times velocity. Because velocity is a vector 1, the linear momentum was vector 2. Angular momentum also similar to linear momentum. We have mass and translational motion, rotational motion. Corresponding quantity is moment of inertia. We have linear velocity in translational motion. In rotational motion, we have angular speed. When we multiply this two, we will get angular momentum L, which is very, very similar in a way. And I has a unit kilogram meter square, which is the moment of inertia. Omega has a unit radian per second, but we are combining radian with other quantities. We don't write radian, 1 over second. So it's going to be kilogram meter square per second is the angular momentum. Yeah, the angular momentum in fact defines again how strong the rotation is. Yeah, if very big angular momentum an object has, it's not easy to stop it. If a small angular momentum, it's easy to stop it. Yeah, it defines you can stop very easily or you cannot stop very easily if an object is rotating with big or small angular momentum. Conservation means to keep the physical quantity constant. There are several every conservation laws in physics. One of them is conservation of electric charge. That's you studied. When you rub a balloon with your hair, electrons in your hair goes to the balloon, but some of the electric charge doesn't change. It transfers from one to another. And also you studied mechanical energy conservation, so potential energy, kinetic energy changes each other. But they don't. Some of them stays unchanged. Also we know this here. And angular or linear momentum is conserved, but there are some conditions for conservation. Linear momentum conservation, the laboratory started, that was the condition was net force to be zero. If net force is zero, there is going to be linear momentum is conserved. And also you studied like a quantity in a equation like this. If some net force acts on an object by some time, which is called impulse, you are going to observe a change in linear momentum. Yani if you want to change linear momentum of a car, you have to apply some net force on the car. How can you apply net force? By pushing the gas pedal. When you push the gas pedal, force acts on the car. How long do you push the gas pedal? Linear momentum of the object increases that way. Or opposite brake pedal. When you push the brake, this time you apply a negative force. How long you apply the brake pedal? You are going to decrease the linear momentum and stop the car after some time. This equation has a rotational formula effect. It's not given in your book, but it's better to understand. Yani net force changes to net torque. Delta T, same delta T. If some net torque acts on an object by some time, this time object's angular momentum will change. Yani there will be a change in angular momentum. Angular momentum is L, delta is change. This net torque can be positive. If it is positive, you are going to see an increase in angular momentum. And if an object is rotating in one direction, if you push it and produce the same torque in the direction of rotation, you will see that it will start rotating faster. Yani L increases. Or if you friction, just like friction. Friction produces a negative net torque. So if some friction acts, or friction force acts sometimes, so you are going to observe there is a decrease in angular momentum, so object will slow down in rotation. So this equation relates net torque can change in angular momentum, even though it's not given in your book, it helps you. If some net torque acts on object, you can make a change in angular momentum. Yani, only one way we have to make a change in angular momentum. What is it? Net torque. Bunu neden söylüyorum? Why I said this? Because you are misunderstanding this equation. L is equal to I times omega. When you check this equation, you see that, oh, they're related. No. Increasing I does not make a change in L. So, that's why I is not related to L. How to make change in omega, you should of course apply some torque. There's not a way. For example. So, I does not make a change in L. Notice. You can make a change in angular momentum only by one method. Net torque. There is no torque. But if net torque 0, there will be no change in angular momentum. If net torque is 0, delta is going to be 0. There will be no change. If no change means constant. L stays constant. This is condition. How can you keep angular momentum constant for a rotating system? By net torque, net external torque to be 0. So, whenever the net external torque acting on an object is 0, the object's angular momentum does not change and stays unchanged.
Torque olmasaydı?
0 olması lazım. If torque is 0, net torque is 0, angular momentum will stay unchanged, it will stay constant. So, if angular momentum stays constant, yani L is equal to I times omega, if this is stay constant, which means net torque 0 of course, net torque must be equal to 0, then I can say this. Angular momentum stays constant. I see that if this is constant, I and omega are inversely proportional. So this is another way. Another way, how can you increase omega? Without changing angular momentum, we can increase omega. How? By decreasing the moment of inertia. Remember the ice skater example. Arms are open. So moment of inertia is largest when your arms are closed. What happens to the... It starts spinning faster. Moment of inertia decreases, angular speed increases. Yani, you can change angular speed by two ways. One of them is net torque. By means of alpha, you can increase the omega. Second one is without net torque, decrease the moment inertia, increase omega. Okay. So, as moment inertia of a system decreases its angular speed, increases to keep angular momentum constant. But these types of questions, friction must be neglected. Because friction produces an opposite directed torque. Like ice. On ice we consider friction to be zero. Or then the question must talk about ice, or it must specify angular momentum is conserved. They have to. Or they should say net torque is equal to zero. So this is the equation for conservation of angular momentum. L initial, L final. I initial, omega initial, I final, omega final. So we are going to apply an equation, a question to this. At 65 kilograms spinning, student spinning on a merry-go-round that has a mass of 525 kilograms and radius of 2 meters. She walks from the edge of the merry-go-round towards the center. The angular speed of the merry-go-round is initially 0.20 meters per second. What is the angular speed when the student reaches a point 0.5 from the center? You know it. As the student is walking towards the center, so distribution of mass gets closer to the axis of rotation. Moment inertia decreases. If moment inertia decreases according to conservation of angular momentum, this is unchanged. If moment inertia of the system decreases, omega must increase it will. If student does opposite, and moves away from the axis of rotation to the edge, this time moment inertia increases, angular speed must decrease. So, but how much? The final angle. We are going to choose this equation. What is the equation? I final initial omega initial is equal to I final omega final. This is the question. This is given. Omega initial is given. This is omega initial. But to calculate omega final, I need to know what is I initial, total systems omega initial, and also I need to know what is my final. I have to calculate them one by one. System composed of two components. One of them is the disk merry-go-round. Disk moment inertia is 1/2 mr squared. So it's going to be 1050. Second component is student body. It follows a circular path, mr squared. Circular motion, going this about an axis, mr squared, it's going to be 260. Total moment inertia is going to be some of them, because moment inertia is a scalar quantity just like mass, we will add that. So, result is 1210 initial moment inertia. Final, moment inertia of the merry-go-round is the same because there is no change in the shape, there is no change in the mass of the merry-go-round, there is no change in the distribution of mass, same everything. That's why this number is going to be as also final case moment inertia for the disk, for the merry-go-round. But students, new positions close, what happens to the R? Decrease from 2 to 0.5. It moves from 2 meters to a point closer, 0.5. No, 60. System final moment inertia is going to be sum of this term. 1050 plus 60, which is going to 1066. After that, you are going to insert them. This is I initial in here, I final in here. Then you will find what is final angular speed for this system. Clear? Do we have a question yet? There's one more problem, but all the problems are similar. That's why I'm not going to talk them all of them. This is, and what we do is no different. So you are going to find systems initial and final moment inertia. After that, you are going to apply conservation of mechanical angular momentum equation. The other one is, we are going to talk about energy. When object is translating, moving in a straight line path, just sliding case, which is called translation motion, kinetic energy is going to be 1/10 squared, which is called translation kinetic energy. But if an object is spinning, it's also in motion, there must be energy related to motion, but rotational motion. This is called rotational kinetic energy. It's going to be 1/I omega squared. Only rotational kinetic energy, only translational kinetic energy, but rolling case, both of them. Translational kinetic energy plus rotational kinetic energy, which is total kinetic energy. We are going to have. If an object is rolling on a surface, we can write the translational kinetic energy, total energy in terms of the coefficient of moment inertia, because we are familiar with this equation from level grade. Which one? 1/2 mv squared. This is translational kinetic energy. You can write for a rolling object its rotational kinetic energy and total kinetic energy by an equation related to coefficient of inertia. So total kinetic energy, which is the sum of the kinetic and rotational and rotational kinetic energy and translational kinetic energy, is going to be C plus 1 times 1 over mv squared. Yeah, if I write this again, I can write it like this. Kinetic energy total is equal to kinetic energy translational multiplied by C plus 1. What is C moment inertia? For example, this. What is C for this? Right, moment inertia equation 1 over 2. This is C. For any shapes is different. Yeah, if you translation kinetic energy multiplied by C plus 1, you will get total kinetic energy. Also, you can write rotational kinetic energy in terms of translational kinetic energy for a rolling object. Kinetic energy translational multiplied by, do you remember this? Yes? If you multiply translational kinetic energy by C, you will get rotational kinetic energy. Everybody knows translation kinetic is 1 over mv squared. So it's easy. It's not involved with rolling case. So we can get very easily by this way. For example, this question. A solid sphere rolls on a horizontal smooth surface at a constant linear speed without slipping. Show that rotational kinetic energy about central sphere is 270 total kinetic energy. A total kinetic energy equation, kinetic energy total muscle, how we can write it? Kinetic energy translational times C plus 1. Peki, rotational kinetic energy is what? Kinetic energy, rotational is equal to kinetic energy translational times C. Divide them to get the ratio. So kinetic energy rotational divided by kinetic energy total. It's going to be total rotational kinetic energy translational times C divided by kinetic energy translational times C plus 1. They will simplify. You got C divided by C plus 1. For any rule object, you can find this way. C is for solid sphere 2 over 5 divided by 2 over 5 plus 1. So numerator 2 over 5. Denominator is 7 over 5. Then you flip it 2 over 5 times 5 over 7. Result is 2 over 7. Then there are several questions like this. You can very easily find them like this way. These rolling cases. And one last topic, conservation of mechanical energy. It's about an object to roll down on a surface from an incline, from top of an incline to the bottom. As this bicycle tire is rolling down, its potential energy at the top converts to kinetic energy at the bottom. But not only translational kinetic energy, total kinetic energy, because it's rolling. So potential energy top is mgh. Total kinetic energy at the bottom is 1 over 2 mv squared times c plus 1. They're equal to each other. When you make them equal, you will get this equation to calculate v at the bottom. 2gh divided by c plus 1. For example, let's apply this. Find what is v for this bicycle tire. So 1.5 kilogram bicycle tire over radius of 0.33 meters start from rest and rolls down to the top of the hill. That is 14.8 meter high. What is the translational speed? Find v at the bottom of the incline. So v is equal to 2 times 9.81 times h is given 14.8 divided by c plus 1. What is c for bicycle tire? It's a tune about symmetric axis. 1. 1 plus 1. 10 root. So it's going to be 12.1 meter per second. And one more thing better to know, If this bicycle tire is on an icy surface, it will not roll. Because on the ice, object does not roll, they slide. All potential energy will be converted to translational kinetic energy only. That's why it will slide very fast. And its translational speed at the bottom is going to be bigger than this. Because in the rolling cases, the potential energy at the top will be converted to translational kinetic energy plus rotational kinetic energy. That's why for rolling case, it's going to be moving down at a smaller speed. They make a sliding case faster than rolling case. Ice olursa rolling olmaz. Only sliding. Mesela böyle bir tip yapabilirsin. A bicycle tire is released at the bottom of a icy inclined plane. So what is the translational speed at the bottom? So you are not going to distance rolling case. You'll take only sliding case. Yani mgh will change 1 over 2 mv squared only. You will find speed greater than this one in this case.
Yani in this case we don't say this Vt equal to that one. We don't use that rule.
Which rule? We don't. Rolling case we can use this one.
Okay, but that case.
If not rolling, V is equal to 2gh only. This, not c plus 1.
Yani if it's say like it's sliding on the ice.
This is the equation.
Okay.
V is equal to 2gh. You studied this last year in free fall.
Do you think they get this question?
But if it is not, I don't think so. But if it is the rolling case, 2gh divided by c plus 1. This is rolling case. This is sliding or falling. Falling case, sliding case or falling case. They make it sliding and falling, because falling is asked in ministry. They ask this. One object is first dropped down, falls. The other one rolls down. Which one is faster? They ask this. Falling case is faster than rolling case. They make it falling and sliding case is going to be reached the bottom with a greater speed than rolling cases. All right.